So I'll try to be brief, quick, and understandable, hopefully. Let's see if it works. Oh yeah, okay, it works, it's just doing good. So, I was speaking about something called twin color, which I will introduce, and how we can use it in a multi-group form. So, first, some motivation. We as computer scientists, we like to solve hard problems, right? And sometimes the problems are so hard that they are even hard when the primitive is bounded, or when the packet is bounded, or even on trees. But we still want to solve them somehow, and want to solve them exactly. So then maybe we can try using some stronger parameter than tree root, right? And that's what people do, especially in bioinformatics and other similar disciplines. And one of the really frequently, by my impression, the most frequently used parameter in this case is vertex color. And you can also use vertex color as a parameter. And it actually works pretty well. So why do people use vertex color as a parameter? Well, it's a big hammer. You can use it. You can use it to break many problems. So what I mean by that is that if you have a graph with bounded vertex color, then chances are your extremely hard problem will become solvable in FPT time if the vertex color is bounded. So that's good. But it comes with a catch, unfortunately, and that's vertex color as a parameter is very restrictive. So what I mean by very restrictive is that the class of graphs which have bounded vertex color is not very rich. So if you want to use vertex color, chances are you will find out your graph has a high vertex color and you will get very slow algorithms. And this is something you want to improve. You want to somehow make this go away, or at least make it at least a little bit better. So the main question is if it is possible to somehow generalize vertex color so that you can still use it to solve all of these really hard problems in FPT time, but at the same time to make it less restrictive on the graphs. Yeah. And there is some intuition why this actually might be possible. So of course graphs with small vertex color are sparse. I don't need to speak about it, that's pretty clear. But on the other hand, all of these practically interesting problems, which I will speak about later in the talk, are solvable also on complete graphs which are not sparse. So this is kind of strange. You use vertex color as a parameter to solve these problems, but they are, even if they are hard on trees, they are somehow solvable on cliques easily. So we somehow want to extend vertex color in this direction. The hope is that this is possible and that we can in this way somehow extend vertex color and make it less restrictive. And there is actually a previous somehow proposed parameter. It was not proposed as an actual parameter, but it has all of these properties. It's called neighborhood diversity. It was introduced by Michael Lampis. And it has a nice definition. I don't introduce it here, but it's really natural, it's nice, and it's useful for dealing with MS1 logic, and then he uses it to actually get some results for MS1 logic on vertex color, and that's nice. But this comes with two problems. The first one is that it's up to exponentially higher than vertex color. So if you have a graph of vertex color, I don't know, k, then it can have a neighborhood diversity of 2 to the k. And that's kind of a jump up, which we don't, a blow up we don't want. And that's not nice, because then we get also slower algorithms. And then also many problems are still open. I mean, because this is not so close to vertex color, I would, what I will show, the twin color thing, it's really close to vertex color. So if you have an algorithm for vertex color, you can easily extend it to twin color. But you cannot do it for neighborhood diversity directly. You usually need to just redesign the algorithm from scratch. So that's kind of another disadvantage of this. So I'll show an alternative, but before I do that, I just quickly introduce what's a twin edge. And that's easy. It's simply an edge is a twin edge if both of its vertices have the same neighborhood, basically. I'll show this. For instance, does it work? Yeah, it does. This is a twin edge because these two vertices have the same neighborhood, excluding each other. That's simple enough. So, and now we say that a graph has, we say that some set is a twin color. Basically, it's just a vertex color which ignores the twin edges. That's what I want to say. Yeah, a twin color is a vertex color which doesn't need to cover the twin edges. And you can also define it in a different way, maybe more natural. It's just basically a vertex color where you allow the non-color vertices to be blown up into cliques. But if you do that, if you just blow the vertices up into cliques, you need to make sure that every vertex in the clique has the same neighborhood. So I'll show again. So this is blowing up thing. So this is a graph with vertex cover 3, and the blue vertices are the vertex cover. And you can take any non-cover vertex and blow it up into a clique of any size. Just make sure that they all have the same neighborhood. That's the way you can generate these graphs of bounded twin cover. And these are the twin edges, right, in this case. These three in the clique. So, and here we can just illustrate a simple twin cover. So for this graph, we only need a twin cover of 2, even though the vertex cover is higher, probably, I don't know, 5 or 6. Because this is a twin edge, so we don't need to cover it, and in this clique, yeah, all the edges here are twin edges, so yeah, so it is lower than vertex cover. It is always lower than vertex cover. It might be the same as vertex cover, but it will usually be lower. Yeah. And so, some properties, if we consider this as a width parameter. The first thing is that we need to make sure that if the twin cover is bounded, we can actually compute it, right? Because if we couldn't do that, we could get to the same situation with clique width was in, where we had all these nice algorithms for clique width, but we couldn't compute the k expressions or the clique width decompositions. So we needed an ORAC. But we don't need it here. Here we just have an FPT algorithm to compute twin cover when it is bounded. And it's actually really simple. You just find all the twin edges, easy. Then you delete them all at once. You have to do it all at once, and then you compute the vertex cover. Okay? So, and we don't need an ORAC, so that's nice. Some other properties, well, how does it fit in with other parameters? Well, yeah, there is the traditional road where you start with vertex cover, then you add paths, then you add trees and paths, then you get tree width, and then you also allow cliques, and then you get rank width or clique width. So this is like the most well-known parameters which are ordered in this way, and this is kind of an alternate route. When you start with vertex cover, when you allow cliques, you get to twin cover, but you don't allow long paths or trees. And then this is of course a subclass of graphs of bounded rank width and clique width. Yeah. And that's for some properties. So now to the core of this. What's it good for? Oh, yeah, no, this is useless. So what's it good for? There are basically 2 things this allows us to do, or maybe actually 3, but let's just stick with 2 so far. So first is that if you have some problems which are hard on clique width or rank width, by hard I can mean NP hard or W1 hard or just in any sense of word hard, then the hope is, and this works, that you can solve it on dense graphs of bounded twin cover. Because even if you could solve it on tree width, these 2 are incomparable, right? So we couldn't solve it on really dense graphs, and now we can, thanks to dense graphs having bounded twin cover. And these are Hamiltonian paths, chromatic number, these 5 problems, but others as well. So all of these are somehow hard on rank width and clique width. Actually, these 2 are even NP hard, and the remaining 3, the bottom 1 and the top 2, are W1 hard or W hard. And all of these are FPT, and the algorithms are really simple because you just basically use what you use for vertex cover. And it works, you just need to do some extra stuff with the cliques. So the second and probably more important thing is that it will allow you to even solve problems which are hard on graphs of bounded path width and tree width. So before we only could solve these problems on graphs of bounded vertex cover, but now we can do more. We can solve it on more general graphs of bounded twin cover. And we actually had quite a few of these problems. So this list is not exhaustive. Right? There are many others, but I'm just one man, so one person. So I only did a few problems and showed that it's not really hard to just extend these algorithms from vertex cover to twin cover. You can see that these are really hard. Some are hard on bounded path width. Some of these, you can add more problems to the list if you want to. So you can even see that this problem is actually NP hard on trees of maximum degree 3. And you can solve all of these in FPT time on graphs of bounded twin cover. And there are basically 2 cases which can happen. Either it's a really easy extension from the algorithm from vertex cover, like it was in these 3 cases. So I won't introduce all of the problems. I need to do that. I'll just speak about some problems. So maybe here I'll speak about graph motif. So this is a problem for bioinformatics, something with gene distinguishing and stuff. I don't know, but it's quite new and seems to be popular. And what's the problem? Well, there's a colored graph and a multi-set of colors. So this is the input. Yeah. And you get this set M and this graph as input. And what you want to find is a connected subgraph of G, which contains exactly these colors. So here, this is the solution in this case. But this problem is really hard in general. And to solve this problem, well, if you just look how the solution works on graphs of bounded twin cover, well, either there is a solution outside of any cover vertices, so then the solution is just in one of the cliques. You can check that in linear time. It doesn't go to any cover vertex, so that's easy. Or it just goes to at least one cover vertex, but then we don't care that it's twin cover, we just solve it as vertex cover. So basically we can delete all of these twin edges because they don't do anything, because we can just use the edges which go out from the, what's it called, from the cover vertex. So it's basically we don't, the fact is that it's a twin cover, not a vertex cover, doesn't add any complexity. Then the other case is that you need to actually redesign the algorithms for the problem. You can't just use the algorithms for vertex cover. So that was the case with, for instance, equitable coloring, but still that's not so hard to do. The measure is quite well structured and it's not so hard to do the algorithms. So for instance, equitable coloring is a problem where we want to find a purple coloring of a graph, but the size of the color classes, it should be color classes, differs by at most one. So you can, so let's say you want to use 5 colors, but then the number of occurrence of each color has to be almost the same, up to difference of 1. So how do you do that? Well, you basically just pick over all the cover vertices and you just have a fixed bounded number of the cover vertices, right? That's what you get for graphs of bounded twin cover. And you do, since the number of colors can be unbounded, you just do that by partitioning this into color classes. So you just partition the vertices into classes with the same color. And you can try all possibilities of this, and then you solve the rest, the non-cover vertices, the coloring of the non-cover vertices, by a Maxwell subroutine. And I won't explain it in detail, but it looks something like that. And if you want to, I'm sure you can come up with a subroutine in like 10 minutes or something. So, yeah. And now just one final result for twin cover. There was this result again by Lampis. Oh, first was MS1. So this is monadic second-order logic is a logic which is used to describe problems. And there's a well-known result that it's FPT on bounded clique with an rank-width. Unfortunately, the table of exponents is really large, or it can be really large. It depends on the alternations of quantifiers. And there's this result by Lampis, again in ISA, that shows that you can do MS1 model checking quickly. By quickly, I mean double exponential. But for MS1, it's quick enough. You can do it always in double exponential time on graphs of vertex cover, to bounded vertex cover. And this extends to twin cover after you do some technical work, some technical stuff. So, just a quick conclusion. I was trying to say that instead of using vertex cover, you can use twin cover. It's a direct generalization of vertex cover to dense graphs, and it's always smaller than vertex cover. And maybe so next time, instead of using vertex cover, you can think about the dense graphs, because otherwise everyone forgets about them and they are sad, and you can generalize your result as well in this way. And just some quick notes about open problems. So the graph layer problems, that's problems which are solved on graphs of bounded vertex cover by an IRP formulation previously. And that's kind of hard to do for twin cover. Right? If you just have an IRP formulation, then yeah, it's not so easy to just get it for twin cover. But if you had to have some structural proofs, then I think it could be done. And there was actually, I think there was a paper by Daniel, among other people, which on iPad this year, or on ESA, which showed how to do cut width on graphs of bounded vertex cover. So hopefully this can be also extended to twin cover. I confess I didn't have time to read the article yet, but I'm hoping this could be somehow. For them this was because we don't have any direct algorithm, just the IRP formulation. Then it would be interesting to see what would be the difference between twin cover and vertex cover on practical graphs, maybe on those graphs from 3-bit library. I have a master student who wants to do a thesis on this, so maybe we'll have some results eventually. And yeah, there was this comment by Hans, which was actually, I think it was by Hans, I'm not sure, about allowing not cliques in the, here we allow basically cliques and non-cover vertices as long as they have the same neighborhood. So we could also allow other stuff which is also easy to deal with, like paths. But this is also future-wide open. So that's